Delighted to welcome Michael Levin to the AI House. Michael is a professor of biology at Tufts University and the director of the Allen Discovery Center, and he's widely regarded as one of the most innovative scientists working today, bridging behavioral science, biology, physics, and engineering. His lab explores and builds biological systems to help us understand the nature of intelligence, agency, memory, consciousness, and life in all its form. So, Michael, thank you so much for taking the time to be here and to talk with us.
Yeah, thank you for having me. It's a pleasure to meet you.
So, I'll let you explain this in more detail, but at the heart of the work is a profound question about embodied minds from biological systems to computational systems. So, how would you describe the focus of your research at the Levin Lab?
So my lab spans from very deep, sort of fundamental philosophical problems all the way, hopefully all the way through to very practical applications in regenerative medicine, engineering, and things like that. And the specific questions that we're fundamentally interested in is how embodied minds can come to exist, scale, and transform in the physical world. So all of us have physical embodiments, which have to follow the laws of chemistry and physics and things like that. But at the same time, it's obvious that at least some agents have a wide degree of a cognitive life, and so we want to understand how that happens in all of its forms. So not just brainy animals, but also cells and tissues navigating all sorts of weird problem spaces that are hard for us to imagine. And once we learn to recognize and communicate with these diverse intelligences, then we get to have interesting new applications in regenerative medicine. So birth defects and regeneration, cancer, aging, all of these things can happen once we can transmit information to groups of cells in a way that allows them to build the things we want them to build.
Okay, I mean, that's very interesting. So, really look at really systems thinking in that sense. And I mean, this goes a bit as well into our next question. We try to understand a bit living intelligence, memory, communication, and these kind of things. And you often start from a very fundamental question, where do minds come from? And you build outward from there. Are you able to give a broad definition of what intelligence is in this broader biological sense beyond just the brain?
Yeah, I mean, I don't think we can give good definitions of what anything is in that sense, but we can certainly have definitions that are useful for research and useful for expanding our own understanding and insight into what's going on. So, for my purposes, I mostly think of intelligence as the ability to navigate some problem space to reach specific goals with some degree of competency in doing that. So reaching the same goal by different means in a context sensitive manner when situations change, some degree of capacity to do that. And I think it's very important to understand two things. First, that if we say that, let's say each of us, let's say we'll start with the uncontroversial case of humans, we have some sort of intelligence, some sort of cognitive capacity. We all start life as a single cell. Okay, we can all trace our existence back to a single unfertilized oocyte, which is a system that looks to be amenable to chemistry and physics. And so whatever it is that we have, whatever mental properties that we have, it is the job of scientists and philosophers to give an account of how that came to be from a single cell. And so understanding that scaling, understanding what is it that chemical systems can do, how is it that they then scale up to the kinds of cognition that we have, both on an evolutionary scale and on a developmental scale, is really critical. And the one thing you learn right away from developmental biology is that there is no magic lightning flash at some specific point where you stop being just physics and chemistry and you start to be a mind. Okay, it's a gradual, continuous, smooth process. So we're looking for stories of scaling, not category, not sharp categories. And so that's the kind of thing that we're really interested in. And in that field, in developmental and biology, molecular biology, and so on, it is often assumed that cells and molecular pathways and tissues and so on, they just do the things they do with no endpoint, no goal, right? And it's said that, okay, the chemistry doesn't know anything, it just sort of does what it does, and then whatever is the result, that's the result. And so it's also really important to understand that it's an empirical claim. This should not be an axiom that we just sort of assume and we all have to believe it, which, although that's how it's often treated, it's an empirical question as to whether those kind of formal models that run on cellular automata, and these kind of open loop kind of things that, sort of by emergence, whatever that is, but by emergence, they have complex outcomes. It's an open question whether those kind of models are really sufficient to understand what's going on, even at the very beginning of life. And I've claimed, and I think research both from our group and other groups show that those models actually don't do very well, and that much better are models not only from cybernetics but from cognitive science. So the question is, can we take models from and concepts from cognitive and behavioral science and apply them outside their normal domain of brainy recent animals, and show that in fact some degree of that, aka intelligence and problem solving and perception and memory and these other things, are actually usefully present in all sorts of minimal systems.
I mean, that's very interesting. I mean, as a definition for intelligence, I think for me it's almost impossible. But also, you mentioned earlier, I mean, you do a lot of research, for example, in understanding and recognizing communication with unconventional intelligences. So, what have you learned about how to engage with systems whose intelligence looks nothing like ours?
The biggest thing that we've learned is to recognize our own limitations and to have humility around the fact that because of our own evolutionary history, we have a very narrow understanding of what kinds of systems can be intelligent and in what kinds of spaces. So it's a little bit like before a good theory of electromagnetism, we were sensitive to a very narrow portion of the electromagnetic spectrum, and we had no idea that these other portions even exist until we had a good theory, and then we made instrumentations. So the same thing is true here. I think we suffer from a huge amount of mind blindness. We find it very difficult to think about how systems at other scales, both temporal and spatial, right? So very fast, very slow, very small, very large, systems at other scales and operating in other spaces. And for example, people often say, well, this is a system that isn't moving around in the three-dimensional world. It's either an AI sitting in a box somewhere, or it's a neural organoid and it's not going anywhere. So it's not embodied, right? It doesn't go anywhere. Well, the three-dimensional space is not the only space in which you can have a body. Biology navigates all kinds of other spaces. It navigates physiological state space and metabolic state space and then anatomical state space. So in all of these spaces and many other weird spaces that are hard for us to visualize, these systems do that loop of sensing, prediction, perception, action, memory, decision making. All of these things happen in these other spaces. So if you want to communicate with these other intelligences, which I think are all around us, we're just very bad at noticing them, you have to have a lot of imagination, and then you have to commit to the idea that communication is a way to test how good you are at recognizing these things. You cannot have philosophical or linguistic decisions about how this is intelligent and this is just a cell. This can't be intelligent, right? You can't say any of that until you've done the experiments. And so the idea is to have an appropriately wide imagination of what kind of system you're dealing with, and then design appropriate tools. And so in my lab, we design specific technologies that allow us to try to share at least a little bit of a world with other systems that may be extremely different than us.
Yeah, wow. I mean, even like thinking about something beyond the 3D space for most people is hard to imagine, but very
Yeah.
interesting. And so I think now I'd like to bring the discussion a bit more to AI, because that's what we're here for. And I want to explore how your understanding of intelligence might help us to rethink of what we're actually building when we create artificial systems. So you've previously said that neuroscience is not really about neurons. Can you elaborate on this? And if we connect this to artificial intelligence, whose core architecture are loosely inspired by neural networks of the human brain, then what do you see as the fundamental limitation of AI when you compare it to real embodied human intelligence?
Well, the first thing that I would claim is that human intelligence is not what we should be shooting for. So, biology has been solving problems via different kinds of intelligence long before brains showed up, and certainly long before humans showed up. And so, in order to really understand what is fundamentally intelligence, we shouldn't be aiming towards brains. We shouldn't be aiming towards neurons. We should be asking what are the policies and mechanisms underlying the amazing ability of biological systems to solve difficult problems in high dimensional spaces, to do adaptive things in scenarios they've never seen before that they weren't prepared for. I mean, biology has an incredible amount of intelligence long before you get to neurons. And actually, pretty much everything that neurons do, every cell in your body does this. This is the mechanisms that neurons use, the ion channels, the electrical synapses, the neurotransmitters. These are ancient mechanisms that have been around for the longest time. And long before your neural networks were using electricity to think about moving you through three-dimensional space, those electrical networks existed in your body, non-neural, that were thinking about how to navigate your body configuration through anatomical space. What shape should you be, right? And how to get there. So this is the basis of intelligence. And I think what the real lessons of neuroscience is not anything specific about neurons necessarily. It's much more about what I call cognitive glue. Cognitive glue is a set of policies and processes that allow competent subunits to align into a larger collective that knows things and has goals and competencies that the parts don't have. So what happens in our brain is that we know things that our neurons don't know. We have goals and memories and dreams and other things that individual neurons don't have because of the ability of bioelectricity to act as this cognitive glue. It makes a network that with very particular properties that allows us to scale the cognitive light cone of individual neurons and become this thing that projects into other spaces, right? Spaces that individual neurons can't know anything about. So this is what I think really the lessons of neuroscience out there about understanding a multi-scale system where, yes, you can study the molecules, but you can also, so you can study the molecular biology of synapses, but you can also study electrical network properties, and you can also do psychoanalysis and psychiatry and things like that, which address the system at multiple levels and understand that talking to the synaptic molecules are not the only important levels in the system. That's the deep lesson of neuroscience, and that can be applied all over the place. And I think that chasing these neuromorphic architectures is really not the way to advance in AI. All the comparisons with humans and with brains, I think it's not the right way to do it.
Yeah, I mean, and so you, like you said, you study now like this multi-agent corporation and goal-directed collectives of cells, actually. And we do see now a bit we're moving in like AI to like to researchers exploring multi-agent, emergent, or self-organizing architectures. Do you see like the parallels between these natural systems that you study and these like agentic economies or these kind of things that we're building with AI?
Yeah. Well, I think there are two things. On the one hand, I think the way we try to build them is fundamentally not the way biology works. So when we build computational systems, we typically have abstraction layers, we have error correcting codes. The whole point is that the higher level that you want to be intelligent should not care or know about what's going on at the lower levels. When you're programming, you never think that your registers are going to float off because the copper is getting too hot or whatever. You like the whole point of a good computer is to isolate you from all of that. Biology does the exact opposite. It knows that the material is ultimately unreliable. Everything is going to get mutated. You never know exactly how many copies of anything you have. And so in biology, everything goes towards creating algorithms that improvise. They don't take the information literally that they have, they improvise, and this is true for memories in our brain as it is for DNA. Embryos don't just do what the DNA says; they actually interpret these things, and that's what gives them the plasticity to do new things. So this idea of emphasizing the saliency of information and the plasticity of its interpretation, not the fidelity, not the error correcting part, is very different, right? And I think until we start building that way, we're not going to be able to reach what biology is actually doing. But there's a flip side to this, which is that I also think that this notion that systems do what we build them to do, and this old idea that we all learn in computer science that you have an algorithm, the algorithm does exactly what you want it to do, and it's a dumb machine, and it's only going to do what you tell it to do. This is what we're now finding is an extremely limiting perspective, and basically, and when we have some very minimal systems that are showing us how this is actually incorrect, and if those minimal systems are doing it, then I'm sure that complex AIs and all of these things are probably doing it too. There are lots of novel properties, and I don't just mean complexity or unpredictability. I mean things that are recognizable by any behavioral scientist. Okay, so protocognitive competencies that arise in systems not because of the algorithm that we put in, but despite the algorithm. It arises in the spaces between. It arises in the things that the algorithm does not prevent them from doing. And so from that perspective, it turns out we are also very bad at knowing and being able to predict what's going to happen, because we don't know where novel collective intelligences get their goals. We have no idea, right? In biology, you can sometimes blame it on evolution, but for these things, we don't know. And so just because we think we've engineered it in a certain way, and we're watching for a certain kind of output, let's say linguistic kind of output, that may not be at all where the intelligence is going or what it's doing, and it may give actually very little clues to what's going on.
Okay. I mean, I have to ask you now, what do you then think of AGI, super intelligence?
Well, I mean, I don't know what super intelligence is. I think that exists on a very wide spectrum. There are many different kinds of intelligence. I don't see any reason why the level that humans have happened to have reached at this point is any kind of a special marker. I think there's lots of room below us. I think there's lots of room above us. Um, I think the things that we're engineering now are in no way like human intelligences, but humans, I don't think, are the metric of all things. I think there are many different kinds of intelligence. And until we get really better at noticing different kinds of intelligence in different spaces, we have no hope of understanding what it is that we're building. In other words, the language communication that we're doing with these systems is easy and obvious for us. That's not necessarily where the intelligence is coming from. And I think the field of diverse intelligence, and there are many people, it's not just me, there are many people in this field that are doing amazing work, that field has not really been connected to AI, and I think it's a huge mistake. I think that AI can benefit greatly from the deep understanding in that field of the diversity of different kinds of minds.
I agree. And then maybe like honing it down to the human individual being that we are, kind of what advice would you give the younger generation to how to train their brains or even bodies, to educate themselves, to stay innovative, creative, and critical thinkers?
Wow. Okay. Well, I don't know. I don't know if I can do anything like that, but I'll give a couple of suggestions. Uh, the first thing I would say is that a lot of the categories that we've been handed down through our education are they're more limiting than they are useful at this point. So these binary categories, when philosophers tell you that you've committed a category error, right? What do you mean cells have memory? Humans have memory, cells can't have memory. Come up with another word. Well, these category errors, these categories weren't given to us for once and for all by God, and that now we have to stick to these categories. The categories should evolve with the science. And what I think the next generation should understand is that we've given you a lot of categories, that sharp categories, that I think are kind of garbage, really. It's like things around organism versus machine, right? Not that there aren't differences, but the idea that these are sharp binary categories, and then you can understand which thing belongs to which category. All of this is nonsense. There's a continuum, and what you need to know is what kind of where any given system is on that continuum, and what does that mean for you when something is more or less along these, like what are the tools that you can bring to this? Are you bringing psychoanalysis? Are you bringing cybernetics, control theory, behavior science, rewiring? Like what how are you going to relate to the system? So these kind of sharp distinctions, even distinctions around data versus machine. So this notion that we know this is the active agent, this is the machine, and then this is the passive data that it operates on. Even that, we've written a number of papers now talking about how even that distinction is actually too limiting, and there are multiple perspectives from which you can flip that. So just being ready to examine the categories that you've been given, and asking what are they doing for you? What's the utility of these things as binary categories, and seeking models of transformation, and talking about understanding that this notion of people talk about proof of humanity certificates, and it's whether something is human or not human. Ask yourself, what does it really mean? What do you really care about when you say somebody is a human? Do you mean the genetics? Do you care about the genetics? Do you mean the specific organs? It has to have natural, like, organs that are primate specific organs. What do you mean? And when your neighbor or your spouse has some percentage of their body or brain replaced by novel technologies, do you care? Is that an issue? What do you actually care about when we say we want to maintain humanity? Like, when as we spread out into the universe and we have to live on other worlds, we're not going to look like this for sure. what is the important part? So asking yourself what do you think is important, and what do you think these kinds of continua mean, and what kind of transformation are you interested in? What do you want to see in the world? Do you want to see this kind of genetics persist, or do you want to see something else? These are the questions they should be asking, and we're not setting them up well with our standard educational system to ask any of that.
Yeah, I mean, it also comes down to a lot big self-awareness and
Hmm.
the emotional intelligence that we need to have for ourselves.
Yeah.
Very interesting. And now my last question to open up the lens a bit. I think I would love to ask, like, which scientific, philosophical, or even spiritual paradigm do you think we may need to rethink over the next 50 years when it comes to science, humanity, and life?
I mean, probably all of them, I would say. I don't know too many that are going to survive completely intact. I mean, everything is being we're coming across the limitations of all of these old formalisms that were forged at a time of much less understanding and imagination, and a lot of we're just coming up with to the limitations of many of these things. And I think the plasticity of what's possible really, I think, breaks a lot of the old categories. And so we're going to need all of it. We're going to need novel systems of ethics that go beyond kind of these binary categories of. I mean, think about it's already been happening. Like think about this category of an adult, right? We all know nothing happens to you on your 18th birthday, and yet to keep the sort of court system going, we've decided that okay, here are adults, and now you get challenged. Now people show up in court with brain tumors, or the Twinkie defense, or with diminished capacity or whatever, and you have to start thinking, but what do we really mean about responsibility and about rights and all of that kind of stuff? So going into the future, all of that stuff, when people start showing up in court with malfunctioning chips in their heads and who's responsible for what, or in fact, forget diminished capacity, how about extended capacity? How about you get somebody now who has 100 IQ points on all of us, and you think, wow, I wouldn't have blamed any one of us, but he should have known better, like that kind of stuff. And so all of these things that we've been familiar with, um, they're going to break, and having to understand how we're going to have some kind of an ethical synthbiosis with beings that are not like us at all, that have that and I don't just mean AIs. I mean, first, like, AIs are not going to be the immediate problem. The immediate problem are going to be humans with implants. It's going to be cyborgs, right, that are partly human, where you're not going to be able to say, oh well, that's a machine, I don't care, that's too easy. That's not where this issue is going to arise first. You're going to have people with a wide range of embodiments already. We have some of that already. We have way more of it. We're really going to have to understand, how do we relate to other beings that are not necessarily like us. And I think it's really important that there's a lot of concern nowadays about mistaking AIs or machines for having more agency than they have, right? Misattribution of agency, and a lot of people are worried that we're going to take these AIs that speak as if there was somebody inside, right? And we're going to falsely attribute these things, and people are going to fall in love with them and whatever. I think the risk is actually the exact opposite. I think human history shows us that we are amazingly prone to zoning in on tiny little differences between us, and saying, okay, here are the real important ones, and these are others. These are not quite like us. They don't need as much, anesthetics in the hospital, or they don't deserve the same, right? We're very good at finding small differences, and like making categories out of it, like in group, out group distinctions. I think that's the real danger. And this is why I think the field of diverse intelligence is so critical, because we have to understand that the kinds of things that we fight about now, the kinds of distinctions and the kind of small modifications that people make to their bodies that get everybody all worked up, this is going to be laughable, even in one generation, compared to what's coming. And we really have to ask ourselves, what is important? What do we find that's really at the core, at the spiritual core of what we want to maintain?
Yeah. Sounds a bit like a complete new societal rewiring, social conduct that we need to learn.
I think so. Yeah.
Well, thank you so much for this really great conversation. Your answers were truly very thought-provoking.
Thank you.
Um,
Yeah.
and
Thank you.
I wish you all the best as you continue with your work. And thank you so much for your efforts in helping to eliminate these complex patterns and explain to us what happens behind the scenes so the rest of us can understand it better and be smarter someday.
Thank you. I appreciate it very much. Yeah, we're all just groping for insight in a brand new field. It's developing very rapidly. So
Exactly.
thank you.
Thank you. And I look forward to have this conversation in Davos to continue.
Yeah, thanks.